Hello viewers and my dear students. Welcome to session 1 on problem 3 on analysis of beams. This here I'll be giving you a demo on simply supported beam with partially applied UDL, that is uniformly distributed load, that is uniformly distributed transverse load, that is perpendicular to the axis, using Ansys Release 14 of Mechanical APDL to obtain bending moment and shear force diagrams. That means in these two sessions, I'll be concentrating only on getting bending moment and shear force diagrams. Okay. Now the problem is this. The problem is this. You please observe. A beam is subjected to partially applied uniformly distributed load as shown. That means there is a beam of 6 meter in length. Okay, 6 meter in length and partially applied transverse load. That is UDL, that is 12 kilonewton per meter or 12,000 Newton per meter. Okay, it is applied only to a distance of 4 meters. Okay, totally the beam length is 6 meters. Okay, determine the following assuming the beam has a rectangular cross section of 0.2 meters width, 0.3 meters depth. Assume E to be 210 GPa, Poisson's ratio 0.27. Determine reaction at their supports RA and RC. Reaction you support. Bending moment and shear force diagram using theoretical methods. That means first you have to do reaction at the support RA and RC by theoretical methods, and also bending moment and shear force diagram using theoretical methods you have to find out. Then use mechanical APDL to verify whatever you have got, whether you are getting the correct answers in Ansys and all that we'll have to verify. Now see here, this is the problem. Okay. Now see here, this is a problem. Right now, this is 6 meters in length. For 4 meter, you have UDL. It is 12 kilonewton per meter or 12,000 Newton per meter. Now you see, you carefully see here, RA plus RC. Let us say at A reaction is A. It is simply supported. No? RA is the reaction at A. RC is reaction at support C. RC. RA plus RC is 12 kilonewton per meter. It is 4 meter. That means it is 12,000 into 4. 48,000 Newton is the thing. RA plus RC is 48,000 Newtons. Then we'll take moments about A, let us say. Okay. Then moment about A, if you take RC into 6, that's what I've done. RC into 6, that is this upward force. Okay. That means anti-clockwise moments, I'm taking positive. Okay. RC into 6 minus 12,000 into 4 is the total load. That is assumed to act at the center. That into 2 you do. Okay. 12,000 into 4, it is assumed to act at the center. That into 2 you do. 12,000 into 4 into 2 you get. That means RC you get it as 16,000 Newtons. Then once you get RC 16,000 Newtons, RA plus RC is 48,000 Newtons. In that way, substituting RC, RA you get it as 32,000 Newtons. Okay. This is how you determine the reactions. Now you see here. See here. You have found out the reactions. Now you see here. Now carefully analyze, because these are all the elementary things what you would have done already in SYM and all that. But it is a sort of revision, and also since it is very important from the subject point of view, you need to know the basics also. In so many interviews and all that, they'll ask you the concepts. See here. For bending moment and shear force diagrams, how to do, I'm telling you. Now shear force diagram and calculations. See here, this is RC. You just now determined, no? RC is 16,000 upwards. Okay, upwards we'll take it as positive. 16,000 upwards. Okay, see here, 16,000 upwards. Okay, that is, if you take any section between B and C, it is only RC. Okay. Up to B, it is only at the right side, you have only 16,000. In that way, it is 16,000. Up till here, it is 16,000. Then you see here, shear force between B and C is 16,000 Newtons. That is, B and C is 16,000. Upward is taken as positive, 16,000. Shear force at A you see here. Upward is positive, 16,000. Minus, you have UDL, no? UDL is 12,000 into 4, 48,000. This is downward is negative. In that way, You see here, shear force at A is 16,000, upward is positive, that is UDL 12,000 into 4 is negative, that is downward force is negative. Shear force at A is 16,000 minus 48,000, it is minus 32,000 newtons. That is here 16,000, here minus 32,000, up to B it is 16,000 only. Since between B and A you have UDL, it is a straight line which connects this point and this point. That is UDL representation of shear force diagram. Okay, this is a straight line UDL you draw, but this is parabolic in case of shear bending moment diagram. Anyway, okay, now once you do this, you know very well one very important thing what you observe here is this shear force diagram is 0 at this point, at Z point, at the point Z. Okay, let it be at a distance of X. The important significance of Z is wherever the shear force 0, wherever shear force is 0, bending moment will be maximum. Okay, let us say shear force is 0 at a distance of X from the left support A. Okay, left support A. Okay, you see here 32,000 upward is positive minus UDL you have no up till here it is 12,000 Newton per meter up to X no. Okay, that is up to 12,000 into X. Did you follow? Upward is positive 32,000. Okay, as you see here RA is 32,000. Okay, RA what you have got is 32,000. 32,000 upward is positive minus downward, that is downward acting forces negative, minus 12,000 is the UDL into X. Okay, if it is 12,000 into 2 I had done, but it is X now, we don't know where exactly the distance. In fact, it is the distance to be found out. 12,000 it is Newton per meter. Let us say it is X meters, 12,000 into X. That means X will be 2.66 meters equal to 0 you do, because the X is equal to 2.66 meters you get. Bending moment will be maximum where shear force is 0. That means at Z you will get maximum bending moment. Okay, this you should know. Okay, now you carefully see here. See here, bending moment at C. Okay, bending moment at C. Okay, bending moment at C is anyway 0. Bending moment at B is RC, that is 16,000 into 2, 32,000. Correct, no? 16,000 into 2, 32,000. Bending moment at C is 0. Bending moment at B is 16,000 into 2, 32,000. Then you go for bending moment at this point. Okay, bending moment at Z. Bending moment at Z is 32,000. That means here, from here you take. Okay, bending moment at this is RA. RA is 32,000 into 2.66. This is 2.66 minus this is here the load is 12,000 Newton per meter. No, 12,000 into 2.66 is assumed to act at the center into 2.66 by 2 you take. Okay, 32,000 into X 2.66 because RA is 32,000. 32,000 into 2.66, 12,000, that is 32,000 into 2.66 minus 12,000 is the UDL. That 12,000 into X, 12,000 into 2.66 is assumed to act at the center. That into X by 2, that is that into 2.66 by 2, you get it as 42,670 Newton meter. That is the maximum bending moment. That is why now at C it is 0, at A it is 0, at B it is 32,000, at Z it is 42,670. Okay, from C to B you join by a straight line. From here it is a parabolic curve. Okay, at A it is anyway 0, at Z it is 42,670 Newton meter. This is maximum here. This you have to show. Okay, what approximately you draw. This is a very good problem from the examination point of view because they'll ask you to find theoretically as well as using answers. This is a very good problem from the examination point of view. Once you do this, these things 42,670 Newton per meter, whatever you got, okay, shear force diagram 16,000 minus 32,000 and all this have to be proved using Ansys. Okay, this we'll do now. Okay, now you see here, I have created a separate log file now, as usual, Gurdat partial UDL. Okay, beam analysis with partial UDL. I am concentrating in this problem only bending moment and shear force diagrams only. Okay, bending moment and shear force diagrams only. Okay, see here, file, list, log file. If you see, it is a fresh log file. Only thing is, I have created a new log file under Gurdat partial UDL and beam analysis with partial UDL and bending moment and shear force diagrams. Okay, that I have created a new title. Okay, file, clear, change title, I have created this. Okay, up till here only done. Now I'll start with the problem. Now this is the way you should do. File, change job name. You give the job name as your name, partial UDL or whatever it is, and immediately give change title and change the title in the way you want. Okay, so that you can easily understand. Okay, then you go for the problem as usual. Preferences, structural. Okay, preprocessor, element type you go, add, edit, delete you go. Okay, add you take, beam you take, 2 node 188 you take, say okay. Okay, you just say close. Then real constant, it does not, this beam 188 does not ask for real constant, will directly put it in sections. Okay, material properties will go. Okay, material properties will go. Material models will go. Okay, structural, linear, elastic, isotropic. Okay, it is 210 E9. Okay, 209 or 2.1 E11. Because in this problem, you see here 210 E9. You see here. Anyway, I'll do this again. You just see. Okay, as you see in this problem, it is 210 GPa. It is 210 into Newton into 10 to the power of 9 Newton per meter square. Correct? No, 210 into 10 to the power of 9 Newton gigapascals into 10 to the power of 9 Newton per meter square. That is why I'll maintain the unit Newton and meter. I'll model it in meter. I'll apply the loads and all that in Newton only. Okay, Newton meter. That is why now I am applying 210 GPa and Poisson's ratio 0.27 here. Okay. Okay, material models, isotropic, 210, E9 I will apply. Okay, Poisson's ratio 0.27. 0.27 you apply. Then say okay. Material, exit you do. Okay, material, exit you do. Okay, then once you do this, section you go, beam you go, common sections you go, take this cross section is this rectangular cross section. In that way, the breadth is 0.2 they are given, height is 0.3 they are given, 0.2 and 0.3 apply, just say okay. Okay, now once you applied this 0.23 and then you have to do the modeling and all that. Modeling you go, okay, create key points in active coordinate system. One is 0, 0, 0 you take, apply you do, 2 you take, 4, 0, 0 you do, apply you do, 3 you do, 6 you do. Okay, see, I created 3 key points and all that. Now, as you see here, you can verify what exactly the key points and all that, and we'll continue. This is session 1 on problem 3, an analysis of beams. We'll continue this in session 2 for the remaining analysis till we get bending moment and shear force diagram until it is verified. Thank you, friends. Thank you very much for viewing. Thank you.